All right, what's up everyone? We are live here. So today what I want to talk about is the 3 levels of binary search. And specifically what I want to do is I want to dig into some of the applications of binary search and some of the ways that you might use it in an interview that are not typical. Most of the time, we use binary search in a very basic way, right? We have an array and we want to find all the values in the array. But there are a couple ways in which we can use binary search and a couple levels at which we can use it that are more involved and that allow us to solve all sorts of other problems that don't actually look like binary search problems. So in this training, I want to go through what are some of these ways that we can approach problems using binary search. So let's go ahead and dig into it. And the first thing that we're going to do is make sure that we're all on the same page here with what binary search actually is and how that works. Because if we don't have that fundamental binary search, then it doesn't matter if we try to do all these other things because we don't know how to do it, right? So if we have binary search, what is that doing for us? With a binary search, let me not do this in red. With a regular binary search, we're going to have some sort of array. So we'll have an array, it's going to be in sorted order, something like this. And the binary search allows us to efficiently find values in that array. And the way that we do this is by repeatedly subdividing. So what we'll do is, let's say that I wanted to find whether 2 is in our array or not. I'm going to find the midpoint of this array first. And in this case, it could be either 3 or 4, but let's say that I find 4. Now, because this is in sorted order, I can look at the value of 4 and compare it to the 2, right? Is 4 equal to 2? If it's not equal to 2, is it greater than 2 or less than 2? If 4 is greater than 2, then what that means is that our value has to be in this half of the array because everything to that side of the array is less than 4, and 2 is less than 4. If 2 is greater than 4, or if my value was greater than 4, I would be looking in the other direction. I would be looking to the right half of the array. And so I do this. In this case, I now reduce this down and I look at this subarray, right? Because I know that my 2 is less than 4. I subdivide it again. And now by doing this, I find, okay, this one is equal to 2. And so I found my value in the array. And this, hopefully, people are fairly familiar with already, right? This is a fairly basic binary search. And I just want to look at the code here real quick so that, again, let's make sure that we're all on the same page. So if we go over to the code here in this case, I have some basic code to do binary search. What I'm doing is I have an input list and I have a target value that I'm looking for. I establish the bounds, right? I'm going to establish the bounds of the initial subarray that I'm looking at as the beginning and the end of the array. And then I'm going to keep subdividing it. So I'm going to find the midpoint in my array, which is going to be, in this case, we're always going to do the low plus the high over 2 is going to give us the midpoint between high and low. And then if that value is equal to the target value I'm looking for, then I found my result. And otherwise, just like I showed, we're going to either go, if the target is less than the midpoint, we're going to look at the lower end of the array. And otherwise, we're going to look at the upper end of the array. And when we do this, we're going to keep repeating until we find that value or we find that that value is not in the array. If we run our code here, let's just look at a very simple example similar to the one that we were just looking at. And we run it. Gotta save it. All right, so in this case, we were searching for 2 in our array, and it is at index 1, right? We want to return the index value of this value in our array. So this is a basic binary search, and this is level number 1, right? This is level number 1 of binary search that we can use in our interviews. But now, this is not very helpful most of the time, right? This is helpful in the sense that, yes, we know how to do it. But it's not helpful because going beyond the most basic level, this is something that is usually going to be implemented for us, right? We're not going to have to actually implement this in our interviews most of the time. We're going to be implementing something a little bit more involved. And so what I want to look at is, how do we take this basic concept and expand it? How do we get to that level 2? And then how do we get to that level 3? Because if you understand that, you're going to be able to use binary search in all sorts of interesting ways in your interviews. So this was level 1. But now let's consider a slightly different problem. Let's imagine that instead of having an array in sorted order, we have an array that has been rotated. And you may have seen this problem before, and I'll actually, before I draw this out, I will let me skip over to here, and let's look at this problem. So in this example, we have an array where the array is sorted in ascending order, but then it is rotated at an unknown index. And so basically what that means is we took some subarray from the beginning of the array and moved it to the end. So in this example we have, you can see that our array is in sorted order. It goes 4, 5, 6, 7, but then it loops around and goes 0, 1, 2. Right? So we moved this subarray from the beginning of our array to the end. And the question is, we want to see, can we still find a value in this array? Right? So as you can see, this is level 2 now, because it is not as simple as what we were doing before, and we're not going to be able to do something quite as simply as what we originally had. So in this case, we had, 4, 5, 6, 7, and then 1, 2, 3, something like that. And we want to determine whether a value is in this array or not. And so let's go back to our basic concept of binary search. Right? In our basic binary search, we divide the array in the middle, and what are we really doing? What we're really doing is we're just trying to identify, does the thing we're looking for, our target, need to be in the left half of the array or the right half of the array? So in this case, let's say that our target is equal to, let's just say 1. Is 1 in the right half of the array or the left half of the array? And the answer is that in our simple version, in our level 1 binary search, that's very easy for us to figure out because we just compare that value. But in this case, we don't know for certain. And so what we have to do is we have to get a little bit more creative and figure out, how do we bound the two halves of our array? How do we bound them and figure out whether our target is in that half of the array or not? So let's think about this. Well, if we look at the array as we have it now, because where is the pivot point? Where is it rotated? It's rotated around this 1, right? So that's the pivot point. And that means that in this other half of the array, in this lower half of the array, everything is in order. Now, the lowest numbers are not over there, but everything is in order. So if we look at this value and this value, we have a range of every possible value that can be in that subarray. Right? In constant time, we can look at that first and last value, and because we know that if I'm looking at this myself, I know that it's in order. I know that the 1 cannot be in that side of the array because it's bounded. Now, if I look at the other half of the array, because this only works if I know where the pivot point is. So if we don't know where the pivot point is, how can we even figure out where the pivot point is? Well, what does the effect of the pivot have? Let's look at this other half of the array instead, where there is a pivot point. So normally, our array should be in increasing order, right? It should go 1, 2, 3, 4, 5, 6, 7. But in this case, because there is a pivot in there, what we find is that this first value is greater than the last value. We find that 7 is greater than 3 because it rolls over, right? It loops around in that subarray. And so because it loops around in that subarray, what values do we know have to be included in this subarray? If there's a pivot point, every value that is greater than 7 and every value that is less than 3 is included in this subarray here. Again, looking at the other side, that was the opposite, right? And I'll do this in a different color. That was, we had between 4 and 7. So it was 4 is less than x, which is less than 7. Right? Everything in there is between 4 and 7. So now we've found two exclusive groupings, right? We have one grouping that is everything outside of, like, that is less than 3 or greater than 7. And otherwise, we have everything, in this case, we could just do less than or equal here. It doesn't really matter for our purposes. But we have the opposite, right? We have everything else. And so what we've managed to do by looking at it in this way is we've still managed to subdivide this array into two discrete pieces. We've managed to subdivide this array, and now with that information, we can say if our value that we're looking for is in the array, it has to be in this half of the array, or it has to be in that half of the array. So what we've done is we've just come up with a better rule to identify where our result has to be, right? It is no longer as simple as, is it just greater or less than that midpoint? We now have to do something more complicated, which is why this is level 2, but we now can see where this has to be. So if we follow through on this, right, we would look at this midpoint first. We would find, okay, let me look at the ranges of these two. So I'm going to see that the pivot point is over on this half, and it has to be greater than 7 or less than 3, and 1 is greater than 7 or less than 3, right? It's less than 3 in this case. So we would ignore this half of the array, and we would repeat this process. Now what's going to happen is we'll go to, let's say that we go to 2, and we do the same thing again. Now when we look for the pivot point, we see again, 7 is greater than 2, so the pivot point has to be in this half of the array. And that means that if we're looking for the value 1, it is either greater than 7 or less than 2. So we can reduce down to this subarray and remove this part. And then we look again and we find the value that we're looking for. Right? So if we go over and look at the code for this, it's going to be similar to what we had before. It's just a little bit more involved. So if we go to the code, let me comment this out. So in this code, again, we're going to start with our low and high values. And now, again, we're going to find the midpoint. It's going to be the same code as we're doing before. We're going while low is less than high. If our midpoint is the target, again, same thing. The only difference is now this, where we're determining whether to make high equal to mid minus 1 or low equal to mid plus 1, we're going to have to make a decision. And we're going to have to do that based on those criteria that we looked at, right? So again, we'll look for, does it contain the pivot? Essentially, it's like, if it contains the pivot, first of all, if the left side contains the pivot, then look at, is it outside of those bounds or is it not? And then otherwise, if it doesn't contain the pivot, we just do the opposite. So again, in this code, it's going to be the same thing. If we run this, we're going to get, now we're looking for 2. So we get index 4, 0, 1, 2, 3, 4. And so we found, by doing this, where that value was by doing binary search. But again, we just changed the criteria by which we're searching on. So that's level 2. This is getting a little bit more complicated. And now I want to look at one more problem that gets even trickier, but still uses binary search and still allows us to solve that problem very efficiently. And that is this problem, where we're given an array and we want to split the array into m non-empty continuous subarrays. So what does this mean? Our question is, we're given an array like this and we want to split it into 2 subarrays. And we want to do that in such a way that it minimizes the sum of each of those subarrays. So how do we do that in a way that minimizes the sum of that subarray, of the maximum sum of all of the subarrays? In this case, we could split this up into 7, 2, 5, which would give us a sum of 11 plus, not 11, 12 plus 2 is 14. And then this subarray would be 18. So we get 2 subarrays, the max sum would be 18, and that's the best way we can do it. Because if we were to divide it this way, then we would get 14 plus 10, which would be 24, which is greater than 18. If we were to do it this way, we would get 18 plus 5, which would be 22, which would also, or 23, which would also be greater than 18, right? So the best way that we can split it up is that way. In this other example, we're given this array, we also want to split it into 2. And so in this case, I believe that we end up with 1 plus 2 plus 3 is 6, and then 4 plus 5 is going to be 9. If we changed it at all, you would see that the maximum would be greater. And so the question becomes, well, how do we do this using binary search, right? This doesn't look like a binary search problem. But let's start to break this down a little bit, because the reality is that we actually can do this using binary search, and we can do it very efficiently using binary search. So how do we think about this? Well, this is the type of problem where I would think about it in terms of, is there a way that I can validate whether a solution is possible, right? If I can come up with a solution, if I can come up with a candidate solution and check whether that candidate solution is valid or not, then I can go check, I can do binary search to figure out what is the smallest candidate solution. And so let's think about how we would do it with this. what would our candidate look like? So in this case, we have an array that's like, what was it? It was 7, 2, 5, 10, 8. M is going to be equal to 2. Our array is equal to this. And the question is, if I have some candidate, like I want to return some value, in this case, the result was 18, right? The result was 18. And if I want to find some solution to this problem, I basically want to say, well, given a guess, I'm going to guess what the solution is. And then I want to see whether that solution is possible or not. So if I say, I'm going to guess that the solution is 25, then all I need to be able to do is say, can I divide this array into 2 subarrays, none of which are greater than 25, or not? If I said my candidate solution is 5, I could do the same. I would say the same thing. Can I divide this array into 2 subarrays so that all of the sums of each subarray is less than or equal to 5? If I can write a function to do that, then I can do binary search, because I just start with what is the maximum possible value and then narrow down from there. So in this case, how do we validate this? Well, we can really, in this case, it's pretty easy for us to write a greedy solution that basically determines for any value, can we divide it up or not into that many subarrays? Because essentially what we do is, let's say that my solution is, let's say that I guess 10, right? I'm gonna basically scan from left to right, and I need to use all the values. And so I have to, this 7 has to be included in one of our subarrays. Now, if 7 plus 2 is less than 10, that could be a subarray that is also less than 10. And so I can keep expanding until I get as many values as I can in that one subarray. Now, if I try expanding again and I add this 5, I see that, okay, well, I got 9 plus 5 is 14. That is greater than 10. And so this is invalid. So what I just found is that, okay, I can make one subarray that is less than size 10. Now I'm going to start over and repeat this process. I'm going to look at this first one. This is less than 10. I expand it out. Now I get this is less than 10, or this is greater than 10. It's 15. So I get a second subarray. And now what I see is that I still have values left that I need to break into those 2 subarrays, but it is going to be more than, like I still have values left that I have to break into those 2 subarrays, but the sum would have to be greater than 10, right? So by determining that this was invalid, I now know that 10 is not a valid solution, so it has to be greater, right? I've done the same thing that we were doing before with our other versions of binary search, but rather than look at some specific value, I'm doing some sort of computation on my whole result. And so now, alternatively, let's say that I said, let's say that I guessed, I'll redraw this so that it's a little less messy. Let's say that I guessed 25, right? So I'm gonna have 7, 2, 5, 10, 8, and my guess is 25. So I'm gonna say 7 is not greater than 25, 9 is not greater than 25, 14 is not greater than 25, 24 is not greater than 25, so okay, here is my first subarray. And now I find that, okay, 8 is the only one left, so that just gets divided into its own subarray, and so now I have 2 subarrays, both of which sum up to less than or equal to 25. Right? So, okay, this is valid, but that doesn't mean that it's necessarily the smallest valid value. Right? I can probably find something that's smaller than 25, which I know in this case is 18. So now I've established an upper bound. And so I know that I'm going to look in that smaller set of numbers. Right? So this is the concept that we're following here, where if we can break this down in this way, if we can look at how do we subdivide our space, in this case our space is just all numbers, right? It's not an explicit array. But if we can subdivide it, then we can narrow down to that target solution. So if we jump over to the code here, here's what the code's going to look like for this. So we have 2 things. First, we implement this valid function, right, which is going to check whether our guess is valid or not. So we pass in our array, we pass in our target value, and our current the number that we can divide it into, which is m, and we pass in the target value that we're searching for. And what I'm going to do is, again, I'm just going to greedily divide this. So I'm going to iterate through and I'm going to say, can I add this to my current subarray? And if not, I reset and create a new subarray. And I just need to find a true or false value. So I'm not going to go through this code in detail, but you can pause the video here and walk through it and understand how this works. But then once we do this, our actual binary search is very simple, right? This should look exactly like what we had before. We need to establish like what is the max value, and so the max sum of any subarray in this case, right? The max sum of any possible subarray would be the sum of all of the values. And then the minimum would be the maximum of a single value, because the minimum sum of any subarray would be we split them all into their own individual subarrays. So we kind of establish this bounding where it's like we have the max, and we have the max is the lower bound and the sum is the upper bound. And then we're just doing this same binary search, right? We establish the mid, and then we just check, is it valid or not? If it's valid, then that means that our number is potentially too large, so we look at the smaller side. And if it's not valid, then it's too small, and we look at the larger side. So if we run this code, let me comment this out. What we'll find is, again, this was our input from before, from the leak code example. So we jump over to here, we run it, and we see that we get the result of 18. And so this is the third level of binary search. This is the level that gets tricky, right? This is the level at which it doesn't look like binary search anymore. But if you understand how to use binary search in this way, if you understand how to apply it, it's going to open up so many possibilities in your interviews. Because there's so many problems where it's easy to validate whether a solution is possible or not, but it's hard to compute proactively what is that valid solution. And so in any case where you want to find like what is that smallest valid solution, binary search is a great tool that you can use. So hopefully you guys found this helpful. I think that this is a really useful framework to think about as you're going into your interviews. I'm going to be back here live next week. We're going to be talking about another topic, so please do join me then. And I look forward to seeing you all next week.